next talk is from Jacob Lotz, who's at Delft, and he'll be telling us about their use of MFOM reduced order modeling for periodic flows and some space-time applications as well. So please, Jacob.
So, yeah, thank you for the introduction. I kind of lost you in the process, so I cannot see you anymore. So please just tell me if something's happening I should know. My name is Jacob in English, also very fine. I work with Ido Akkerman, which is my supervisor. Maybe some of you know him. And I'm in the ship hydromechanics department of Delft University of Technology. And my presentation will be on computation and reduced order modeling of periodic flows with application to hydrofoils. So the background of our project is basically about the energy transition. So in the Netherlands, we have a lot of water, as some of you might know. And the idea is that we can actually use this water for high-speed transportation. And we can do this by means of hydrofoil crafts. So they are comfortable, they have less resistance, they require little infrastructure, they just require water. And they can reach speeds up to 70 kilometers per hour, which is very fast for a ship. So this is basically a schematic representation of one of the ships. But these ships have like several problems. And one of those is we need improved stability because we are going this fast. We have to make sure that we have the right lift at the right foils. And we have to improve the actuators. So basically the system that makes sure that we have enough lift at certain hydrofoils. So we basically need fast computation of lifts of these systems. And we want to do this with projection-based reduced order models. So yeah, to give a short introduction of these systems, so we have a linear system over here, which is what we call a full order model. We can find this by, for instance, discretizing the Poisson equations. We'll get this linear system. But this, of course, for Poisson equations will be very easy to solve. But if we are solving, for instance, Navier-Stokes equation, what we are going to do, it will get really expensive easily. So what we are going to do is we want to approximate the solution with a solution basis and a number of reduced order model variables. So we find the solution basis by sampling a solution, for instance, in a certain parameter space. So for instance, in the Navier-Stokes case, this could be the Reynolds number or a feature of, for instance, a hydrofoil. And then we use this to find a basis. So for instance, a POD base, we just apply a POD to the snapshot matrix. And then what we do is we have to find a reduced system of equations. So basically, we first approximate our solution with the basis we have. Then we apply, for instance, a Galerkin projection. And then we have our reduced system of equations, depending on the size of this phi hat. And the idea is that this size is much smaller than our full order model. So for a full order model, you can think of, let's say, 10 to the 6 or 10 to the 7 number of variables. And the reduced order model really aims of 10 to the 1 or 10 to the 2. So hopefully less than 100 variables for this system. But for these models, at least, we want to avoid integrating over a large term domain. So to reduce computational requirements even further, but also to avoid an unwanted phase shift in time. So this is something you can see in the graph here. In the black dotted lines, you can see the full order model. And in the colored lines, you can see the reduced order model. And upon the integration in time, you can see that there is a phase shift. So for long time integrations, we are going to have a problem. So what I will be telling you in the remainder of the presentation. So I'm going to explain what kind of assumptions we made in the full order model to how we apply some tricks to reduce these computational burden and solve these problems. And then I'm going to explain how we created the full order model and show some results in the meantime. So basically what we are going to do is we aim to simulate only one period of a periodic motion. And then, as I will show later, this system will become a boundary value problem instead of a initial value problem. And then we are going to create the time periodic reduced order model. So I will give you more details later, but now you kind of have an idea what's going to come. And in the project, we use MFEM and LibROM. I think LibROM is also a library by Lawrence Livermore National Labs. And our code Delphi heavily relies on both these libraries. So yeah, basically it's a wrapper around those two libraries. Yeah, maybe I was a bit too quick about this, but we are really going to look about in periodic flows here. So one of the assumptions we are going to make is that influences, for instance, for waves on hydrofoils, they can be assumed to be periodic. At least we can get away with making the assumption that these are periodic. And these periodic flows, they are not that hard to find in our world. So this framework I'm going to present is going to be much wider applicable. So for instance, these are tidal energy wave converters, or just wind energy converters, hard flow or propeller flow, for instance. So normally, if you would compute time periodic flows, you would start with an initial condition, which you have defined on a boundary omega with some, in our case, we have an inflow boundary and an outflow boundary, and we have something with, for instance, periodic motion. So this will be a periodic problem. And what we do is we find an initial condition, we have an additional condition and integrate into time until we find a periodic solution. So in our case, we use the Navier-Stokes equations. Yeah, I think most of you will know what's going on here. So basically, what I'm now to explain is the trick we are going to apply. So normally, you start with an initial condition, integrate into time, and at some point you will find a periodicity, flow periodicity, that your flow periodicity criterion is satisfied, and you will stop the simulation. But what we want to do is we only want to simulate one period. So we don't have this hassle of all these variables we have to solve here, but we are only going to solve what's actually important for us. And we are going to do this in the space-time domain. So normally, most discretizations are the semi-discretization. So you would have a different discretization for space than for time. But in the space-time discretization, you treat them both very similar. So you can see time as just another direction in your mesh. So in a two-dimensional mesh, it would be the third direction would be time, and in a three-dimensional mesh, the fourth direction would be time. And that's also why I'm also very interested in 4D mesh developments in the MFEM. And this is where we are going to apply the trick. So in this space-time domain, we are going to apply a periodic boundary condition in time. So for instance, this is the start in time, this is the end in time, and we're simply going to say that both these solutions are going to be exactly the same. And now we can replace our initial condition with this periodic boundary condition. And something interesting has happened because our initial value problem becomes a boundary value problem. So our time-dependent problem behaves actually like it's very similar to a steady problem. And this will have some benefits later on. Yeah, we solve our model, of course, weekly, and it consists of 4 parts. I will just go over them quickly. I will skip the details for the sake of time. We have Galerkin times, we have pseudo-transient times, we have use variational multiscale stabilization, and we use weak PCs to solve the flow around the body. I think it's interesting to look at 2 features. I think the first one is that in this framework, you can actually account for time-dependent small scales in the same way as we can actually do for spatial small scales. That's what happens here. But the other thing is maybe a bit interesting for more of you is we use pseudo compressibility, which is some kind of with a term you can just add in your pseudo time problem. And basically this term will converge to 0, and it depends on the artificial speed of sound. And this sped up our simulations with at least 4 times. So this influenced our matrix very beneficially. So I'll be showing a numerical experiment of this framework now. So we are going to look at periodic flow about a pitching hydrofoil. So pitching is basically making a motion around its center of mass, rotating around the center of mass. And this is going to be a sinusoidal motion, but at a very low Reynolds number, because it will be a bit easier to solve. And we are discretizing our domain using isogeometric analysis. So this is basically the NURBS extension part of MFEM. And this is also where I can explain what an actual C-mesh is. So this is a C-mesh, and what the feature of the C-mesh is, basically it's a mesh wrapped around an object. So you have a circular shaped inflow region, and this region, of course, is very not interesting. So it's no problem that you miss these parts. But you have a very large outflow region. This is where interesting flow features will happen. Another benefit is basically that you can, using this NURBS discretization, you can nicely wrap your NURBS around the hydrofoil. So you get a very smooth mesh around this hydrofoil. So we discretize our spatial domain and our temporal domain using second order NURBS. So this is, we are going to look at a 2-dimensional problem, and the third direction is actually time. And the benefit is that we also have this high continuity in our time direction. So we won't need too much control, like too much information in time to get a good solution. So a solution would look something like this. We have a velocity in X direction here, velocity in V direction here, and velocity in P for pressure here. And I'm actually showing you only one period here. So this is, the video loops several times, but as you can see here, we are actually looping over the Z coordinate, and it starts over when I think it's reached 8 or something. That's the end of our domain. So I'm really showing you only one period here, and it keeps continuing in time. And another interesting feature of this space-time fully NURBS discretization is that you can also in the post-processing apply some tricks. So over here we are comparing our results with results from another source. You can see a very good agreement. And our results are in green, and they are a curve. And this is on purpose, because in our post-processing, we can actually determine our force as being a NURBS curve. So this is also a continuous force output we are getting. So the next part of this presentation, I think I have to speed up a bit. I think I kind of already explained this. So we are going to look at the reduced order model. So this previous model I showed you, it's expensive. We really want to speed up this. So this is our Four model system of equations, and we are going to apply the same trick as I did before. We are going to approximate our solution with a velocity and a pressure basis. And the idea is that the number of variables we have here is much, much smaller than we have in our original full order model. Like really, I'm currently using models with 15 variables just to solve my full space-time problem. Yes. So this is I'm going to show you some results here. I think this is not that interesting. What I'm going to show you here is that I'm gonna I have like trained my reduced order model. So I found a basis of my reduced order model just by changing the period of my simulation. So the loopy figure I showed you some slides back ago, I'm going to change the amount, the size of the extrusion in Z dimension. And for some people who are familiar with projection-based reduced order models, this is one of the bases we are getting for our solution. So it's very non-physical. It shows you something about dominant flow characteristics you can find, but it's nothing physical at all. So we are going to construct our like basically reconstruct our full order model solution using a basis like this. So in our model, we have a reduced order model for space and time. So that's why we can, in the end, can speed up this much. So this is a actual solution. So this is physical, where we again have the velocity in x1 or x direction and y direction for velocity and pressure. And we are getting very small errors. So I think for this simulation, I have a speed up of about 50 times compared to the full order model. And I have very small errors. So errors of about 1%. And this speed up is going to be even more faster in the future, as I haven't implemented hyperreduction yet. So there is still some improvement possible in the speed up. But then, of course, I think in a presentation you can not only bring the good news, but you should also say something you should improve. And these are the force curves. So I showed you a force curve before a couple of slides back, and this is these are the forces compared of the full order model and the reduced order model system. And yeah, you can see that there's no match at all. So this is something really you have to look at and improve, because if we are in the end able to compute such forces over one period and relate them to forces on these hydrofoil and be much faster than the full order model system, we can even do these computations real time while this vessel is carrying passengers and blasting over the river, and have even more improved control of this vessel. So as a wrap up, I showed you the full order model, which is time periodic in space-time. We have only one period as time domain because we use this time periodic boundary condition. And now it's more like a boundary value problem. And we have matching results with the literature. For the reduced order model, first test case shows very small errors for flow fields, but large error for forces. But we really have to apply this for more challenging tasks and more challenging test cases to see what is the potential here, and improve the quality of the forces and finish the implementation of this hyperreduction to have an even, I think we can have speed ups up to 500 if we get this. So if you have ideas, please reach out. If you want to know more about this space-time problem, you can find it here. It's still under review, but you should be able to find it on arXiv.